Hello everyone, in this video we are going to discuss about PN junction diode. The PN junction diode is formed by connecting two semiconductors. One P-type semiconductor is connected with one N-type semiconductor material. In P-type semiconductor material, majority charge carrier is holes, and in N-type material the majority charge carrier is electron. In P-type material the minority charge carrier is electron. Whereas in N-type the minority charge carrier is holes. This is the symbol for PN junction diode. This is the positive terminal of PN junction diode, and this is the negative terminal of the PN junction diode. When P-type material and P-type semiconductor and N-type semiconductor are joined in this manner, the minority charge carriers of P-type material, that is the electrons, will move towards the PN junction. This is the PN junction. So the electrons move towards the PN junction. Similarly, holes, which are the minority charge carriers in N-type material, also move towards the PN junction. This positive and negative charge at the PN junction forms a region called depletion region. This depletion region acts as a resistance for the flow of current through this PN junction diode. This depletion region acts as a resistance for the flow of current through this PN junction diode. There are three biasing conditions. First one is no bias, that is no external voltage is supplied to the PN junction diode. Second one is the forward bias, and third one is the reverse bias. So second one is the forward bias. In a forward bias, the positive terminal of the PN junction diode is connected to the positive pole of the battery, and the negative terminal of the PN junction diode is connected to the negative pole of the battery. P-type material is connected to the positive pole, and N-type material is connected to the negative pole. Since the positive is connected to the P-type, the holes of P-type material, the majority charge carrier holes, are repelled by this positive charge and move towards the depletion region, and the electrons, which are the majority charge carrier of N-type, is also repelled because of this negative terminal of the battery. It is repelled towards the depletion region. This reduces the width of depletion region. In this case, it reduces the width of the depletion region, and at certain voltage the depletion region vanishes and the current flows through the PN junction diode. Let me repeat it once again. The positive pole of the battery is connected to the P-type, and the negative pole of the battery is connected to the N-type. Since the positive pole is connected to the P-type, the holes of the P-type semiconductor material are moved towards the PN junction. Similarly, the electrons in N-type material are also moved towards the PN junction. Since the majority carriers are moved towards the PN junction, the potential barrier, that is the depletion region that appears at the PN junction, reduces its width. The width of the depletion region reduces. At certain voltage, the depletion region vanishes and the current flows through the PN junction diode. The voltage at which the current starts to flow through the PN junction diode is called as cut-in voltage. Next one is the reverse bias condition. In reverse bias condition, the P-type semiconductor is connected to the negative pole of the battery, and the N-type material is connected to the positive pole of the battery. N-type is connected to the positive pole of the battery. In P-type, we know that the majority of charge carrier is holes. So the holes will be attracted. The holes will be attracted by this negative pole. So the majority charge carriers will accumulate at this point, and the minority charge carrier will accumulate at the PN junction. Similarly, in case of N-type material, the electrons are attracted by this positive pole of the battery. So the electrons are accumulated at this N, which are the majority charge carriers, whereas the minority charge carrier, which are holes in N-type, are accumulated in the PN junction. In this case, the width of the depletion region increases. The width of the depletion region increases, and as a result, the resistance for the flow of current through the PN junction diode also increases. The first is the zero bias, that is no external voltage is applied. This is the VI characteristics, voltage current characteristics of the PN junction diode. In x-axis voltage will be plotted and y-axis current will be plotted. Why we are taking voltage in the current and voltage in the x-axis and current in the y-axis? Generally the parameter which is taken in the y-axis should be dependent on the parameter that is plotted in the x-axis. Current, the amount of current that flows through the PN junction diode depends on the voltage that is supplied across the PN junction diode. The parameter in y-axis is dependent on the parameter in x-axis. First one is the zero bias condition, no external voltage is applied, which implies that the potential barrier, when there is no potential difference between the two ends of the PN junction diode, there will not be any current flow through the PN junction diode. Next one is the forward bias condition. Positive terminal will be connected to the positive pole of the battery and the negative terminal will be connected to the negative pole of the battery. Till the cut-in voltage, the amount of current that flows through the PN junction diode will be minimum, and after the cut-in voltage, the amount of current that flows to the PN junction diode increases in this manner. The cut-in voltage for a silicon diode, if the type of semiconductor being used is of silicon, then the cut-in voltage is 0.7 volt. If the semiconductor material is of germanium, then the cut-in voltage is of 0.3 volt. This is the case for forward bias. The current grows slowly when the diode is under forwarding bias. Initially there will be no current because there will be a depletion region which acts as a resistance for the flow of current. When the forward bias is applied, the width of the depletion region reduces, so the resistance reduces. As a result, the current increases linearly. Till this point, cut-in voltage, the current increases linearly. After the cut-in voltage, that is, the depletion region is completely vanished. There is no more depletion region. In this case, the amount of current will be maximum. Till cut-in voltage, the amount of current will be linear to the voltage. After the cut-in voltage, the amount of current flows through the PN junction diode will be maximum. This is the case for forward bias condition of PN junction diode. Next is the reverse bias condition. In reverse bias condition, when the depletion region increases, an electric potential is set up across the depletion region, which increases the kinetic energy of the minority charge carrier. In a PN junction diode, in depletion region, the minority charge carriers will be accumulated. The minority charge carriers will be accumulated over here. When this depletion region width increases, the kinetic energy of these minority carriers, both the electrons in p-type and holes in n-type, the kinetic energy of these minority carriers will increase, and as a result, the amount of current will also increase in the case when the depletion region is completely broken. Initially, there will be small amount of current called the reverse leakage current. After breakdown voltage, the amount of current will increase to the maximum. After breakdown voltage, the amount of current will increase to maximum. This breakdown is because of the increase in kinetic energy of the minority charge carriers. This breakdown is because of the increase in kinetic energy of the minority charge carrier. There are two types of breakdown called Zener breakdown and avalanche breakdown. In Zener breakdown, when the diode is reverse biased, the kinetic energy of the electrons increases. When the kinetic energy increases, the electrons tend to move at high velocity. The electrons which move at high velocity collide with other electrons in the PN junction. Thus, collide with other atoms. When an electron collides with the other atom, it breaks the bond between two electrons. As a result, free electrons are generated. As a result, Thus, reverse saturation current flows through the PN junction diode. This is called as Zener breakdown. In Zener breakdown, when the diode is reverse biased, the kinetic energy of the electron increases. Since the kinetic energy increases, the electrons move with the high velocity. The high velocity electron collide with the atom. The high velocity electron collide with the atom. When an electron collides with atom, it breaks the covalent bond between electrons in that atom, thus creating more number of carriers. This leads to reverse saturation current. This is the case of Zener breakdown. In case of avalanche breakdown, when high reverse voltage is applied across the diode, similar to the case of Zener breakdown, the kinetic energy increases, the electrons collides the atom and breaks the covalent bond, thus two more free electrons are generated. Two more free electrons are generated. These two electrons collide with other atoms. This electron collide with one more atom and this electron collide with one more atom. There will be a breakdown of covalent bond which generates two electrons each. Thus, at the end of second stage, there will be 4 electrons. This is called as avalanche breakdown. The number of charge carriers generated will increase rapidly. This is the case of avalanche breakdown. The knee voltage for Zener breakdown is less than the avalanche breakdown. Avalanche breakdown will occur only when high reverse voltage is applied. Only when high reverse voltage is applied, avalanche breakdown will occur. In case of low reverse bias voltage, Zener breakdown will occur. Both these two types of breakdown, Zener breakdown and avalanche breakdown, takes place in Zener diodes. Both of these breakdown occurs in Zener diode. Generally, Zener diode is used in voltage regulators and it is used for many other applications. Thank you.